This is the first video for part 5 from the textbook. And this unit and even this lesson will create an important bridge for us from the tools we studied before this unit to the things we'll study after this unit. So I wanted to overview this course again. So we identify a population and we draw a random sample. That sample can be drawn using an SRS or a simple random sample. It could be a stratified sample or a cluster sample or a systematic sample. We get some kind of random sample, and then we collect data from that sample. It could be quantitative data, and we can look at means and standard deviations or medians and IQR. We can also draw distributions like histograms or dot plots or stem and leaf plots. If the data we collect is categorical, we can look at bar charts and frequencies and other proportions from that data. Okay, now again, the goal of statistics is to draw conclusions about our population. Okay, in other words, to take it back and say, well, I think about this percent or about this is roughly the mean for the population, and I have a certain degree of certainty with that conclusion. Okay, so this video is focusing on chapter 18 about sampling distribution models. By the end of this video, you should be able to define a sampling distribution, and you can explain the sampling distribution model. Okay, you should also be able to state the assumptions and check the conditions for this model and draw and label a sampling distribution for a proportion or for a mean. And you can also explain something called the central limit theorem. In November 2005, the Harris poll surveyed 889 adults, which is a pretty big sample, and found that 40% of adults believe in ghosts. At almost the same time, CBS News polled 808 adults, again a very big sample, and found that 48% of adults believe in ghosts. And we begin to wonder, why is there a difference between these two percents? How can two groups ask the same population the same question and come up with such varied answers? Okay, and we're assuming here that they did do a random sample and that everything about their methods were correct, but they still came up with different percents. Now, the truth is, in November 2005, there was some exact percent of the population that believed in ghosts. And we don't know what that is. That's why we're doing this study. Okay? But we can think about natural variances that happen in our sample as we pick a random sample. We may just get a different group of people. Okay? Now, for our discussion in this chapter, we're going to assume that the true percent of people in November 2005 that believed in ghosts was 45%, some number in the middle. Okay? And we can think about just if you gather a random sample of 800 people, how you might get slightly some differences between each sample. Okay? So the Harris poll may have gathered a sample that happened to be over here, and the CBS News may have happened to get a group that was over here, but they're just different samples that you can pull from the same population. Okay? And that leads us into the idea of a sampling distribution. Okay? The sampling distribution is not the distribution of one sample. Okay, that's a samples distribution. This is a sampling distribution, and it is the distribution of all possible samples. Okay, now the center of the sampling distribution is P, the true proportion in the population. Okay, but what about the standard deviation? Last chapter, we learned about the binomial model and found that the standard deviation of the number of successes from a sample of size n depends on P, the probability of success. So this part of the equation right here should look familiar to you from the binomial model. Okay, but we are looking right now about the standard deviation from the proportion of successes. So we divide that number by n, and we get this equation by simplifying. Okay, so that is the standard deviation of the proportion of successes, or the standard deviation of the sampling distribution. Okay, so the sampling distribution for the proportion of people who believe in ghosts, assuming that it is 45%, okay, is the square root of 0.45 times q, which is 0.55, divided by n, the sample size, and we get a standard deviation of 0.0175, okay? Or filling out our sampling distribution, it is down here below. Okay, so a statistic might vary from sample to sample. Okay, this is called sampling variability. Okay, this is the varying that happens from sample to sample. Okay, another common term, it's called sampling error. Okay, which is kind of a confusing name when it's not even an error at all. Okay, just the differences from sample to sample is called the sampling error. Okay, so before you can use any model, you must make some assumptions and check some conditions. Okay, and there are 5 of them. Okay, first, the independence assumption. We must assume that sampled values are independent of each other. Okay, and that's necessary for our standard deviation equation. That was true for the binomial model as well. Okay, the sample size assumption. The sample must be large enough. Okay, you can't have a really small sample and it wouldn't work out. Okay, the randomization condition, the data must come from a randomly selected sample or a randomly assigned experiment to be free from bias. Okay, number 4 is something called the 10% condition. Okay, in order to sample without replacement, we can't sample more than 10% of the population. Okay, and the last one is called the success failure condition. Our sample must be big enough that we can expect at least 10 successes and 10 failures. Okay, those are the assumptions and conditions in order to use a sampling distribution model. So here is the purple box from the textbook about the sampling distribution model for a proportion, provided that the sampled values are independent and the sample size is large enough. The sampling distribution has a mean of p and a standard deviation of the square root of pq over n. Okay, so let's kind of bridge and talk about the sampling distribution for a mean. And I want to use a dice experiment. So here is a dice applet that I found online, and it will simulate rolling a dice. Okay, so I roll a dice, I get a 6, I roll it again, I get a 5, I roll it again, I get a 4, and then a 6, and then a 3, and then you can keep rolling it over and over again. Okay, and I'll just, for sake of time, roll 100 dice. So it's rolling 100 dice for me and giving me the distribution. If I do it again, it'll begin to look more and more uniform, which shouldn't be surprising for us because that's the natural distribution for one dice is uniform. Okay, if I do 2 dice and roll, whoops, that's 2 dice and roll, I get 4 and then I get 10 and then I get 5 and you keep rolling, eventually it'll look like this distribution here in the back. Okay, it's kind of peaked in the middle. It's unimodal and symmetric, but as we add more and more dice, you'll see it'll follow this blue distribution. As we add more and more dice, it begins to look familiar to us. It begins to look like the normal model. Okay, and that's a really important finding because if you take 1 dice, it is not normal. Okay, it's not the normal model, it's a uniform distribution. But as you add more and more dice, it begins to look more normal. Okay, and that leads us into something that is called the central limit theorem, which is the fundamental theorem of statistics. Okay, a really, really foundational idea for statistics is the sampling distribution of any mean becomes more nearly normal as the sample size grows. Okay, all we need is for the observations to be independent and collected with randomization. Okay, the population distribution doesn't matter. Okay, and that's what's called the central limit theorem. And I want to give you another example of this besides just dice. So there's another applet online that kind of models. Now here's a normal model. If I take samples of size, let's have actually be a larger sample. Let's have a sample size of 20. So if I take 20, a sample size of 20, and from that sample I find the mean. That's the mean from the sample of 20. And I take a different group, a different sample of 20, okay. Now I'll go a little faster. So if here's 5 more and 5 more and 5 more, or just be really quick and do 10,000 of samples like that, okay? Or even, several thousand. So it looks a little more normal. Okay, that's not surprising because the population itself is normal. Okay, but what if it was some really random distribution that's not normal? It's like really crazy, like that. Okay, would you expect the same kind of normal distribution from the sampling distribution? Okay, that's not from my sample. If I take my sample, will kind of be similar to the population, but the sampling distribution, the means from those samples, so here's, if I animate this, this sample data will kind of mirror what the population is, but as I take the mean from that and look at the distribution of the means, it'll look pretty normal. Okay, even with a really strange population distribution, the sampling distribution of the means begins to look more and more normal, which is a crazy finding. It wasn't believed for a long time in mathematics, but eventually they found that it was true. Okay, that the mean of a random sample of a random variable whose sampling distribution can be approximated by the normal model, the larger the sample is, the better the approximation will be. Okay, that leads us into a discussion about the assumptions and conditions for the central limit theorem, and also for a sampling distribution for a mean is a similar group of assumptions and conditions. They still need to be independent. The sample size still needs to be large. They still need to be taken from. It still needs to be taken from a random sample. The 10% condition applies. The new one is this large enough sample condition. Okay, and the sample needs to be large enough. And the truth is, if we know that our population is symmetric and unimodal, we can get by with a smaller sample. The more skewed or more unusual that our population is, the larger our sample needs to be. So it's not like this one, rule of thumb, but the textbook tends to use the number 30 as kind of a good rule of thumb. 25 or 30 tends to be enough for most samples. If it's highly skewed, we need a bit more. If the population is normal, we can get by with a little less. But 30 is kind of a good rule of thumb to be large enough. Okay, so we would assume that the center for a sampling distribution for a mean would be what the mean of the population is. Okay, but what about the standard deviation? Okay, in the last example about proportions, we kind of got that through the binomial model because they were related, but the mean and the standard deviation are very different when you're dealing with means. Okay, now there's a math box in the textbook that kind of derives this equation, but essentially it boils down to a very simple equation of sigma over the square root of n. Okay, so the sampling distribution model for a mean, or the central limit theorem, says that when a random sample is drawn from any population with the mean mu and standard deviation sigma, its sample mean has a sampling distribution with the same mean mu, but whose standard deviation is sigma over the square root of n. Okay, no matter what the population or random sample comes from, the shape of the sampling distribution is approximately normal as long as the sample size is large enough The larger the sample used, the more closely the normal model approximates the sampling distribution for the mean. Okay, and that kind of wraps up this chapter about a sampling distribution, the distribution that comes from all possible samples. Okay, you should explain the sampling distribution model and state the assumptions and conditions for the sampling distribution model. There are 5 of them. Okay, you should also be able to, I'd recommend that you memorize those 5, by the way. Okay, you can also draw and label a sampling distribution for a proportion and a mean, which means you know what the mean and the standard deviation is, whether you're dealing with a proportion or with a mean. Okay, and also you can explain the central limit theorem. Okay, thank you so much for watching.